Hello and welcome to another installment of our use of Jupyter Notebooks to have a look at problems in financial economics and to develop some basic numerical programming skills. In this tutorial, we'll be looking at the law of large numbers, which is very important for thinking about diversification effects in portfolio selection. So it's nice to develop some intuition about what's going on there beyond the optimal portfolio theorems. But it's also a useful way to practice drawing random numbers and doing something with them, a very simple piece of modeling, and then drawing a picture to look at the output, which is our sort of basic methodology for using scientific programming to investigate questions in economics. So what we're wanting to do is look at what happens to the distribution of the sample mean as the sample gets larger and larger. And what should happen, according to the law of large numbers, is that distribution should collapse into around the mean. So basically, when you take one draw, you get a lot of noise. When you take 10 points and you average them, you get a much better draw, and so on. And we can see how much better by repeating that, doing numerical experiments for different size draws and seeing what happens. You can see the basic instructions there from the tutorial problem. Let's start, as always, by loading up the libraries, the packages that we need. Now, we could do this in one go, and we will eventually get to do that, get one piece of code that does all of this, but let's develop our code in simple steps so we can see what's happening, and this allows us both to learn programming better and also as an approach to developing code. It's good to develop in little pieces, make sure they work before assembling them into large programs. When you have a large program and it doesn't work, then you don't really know where to look for a problem. So let's start off. We're going to want to draw 500 samples of different sizes. Let's start with a sample of size 1. That's good because we know exactly what that should look like. It should look like 500 normally distributed numbers. And what normal distribution are we going to use? We want to use this one here with a mean of 0 and a standard deviation or variance of 1, the so-called standard normal distribution. And this is our random number generator, NP random with the normal option. If we wanted a different distribution, there are different ones available in that package. So we're going to generate random numbers from a distribution with a mean 0 and a variance of 1, and then we're going to draw 500 replications or 500 experiments, and each experiment will have just one number in it. So that will produce an array, sample 1, which will be 500 by 1, or at least that's what we hope. So let's do that and check what we've got. So in fact, we have got a mean that is pretty close to 0, but not exactly 0, and we've got a variance which is close to 1, but not exactly 1, which is what we expect to happen because these are only experiments done in the computer. They're not going to be exactly what we would like to see. And let's just check here that we actually got the right size. Yes, 500 by 1 were the number of elements in the mean. And I kind of skipped ahead there, but remember, NP mean is a function that calculates the mean of something, sample 1, and NP var calculates the variance of something, sample 1. So that calculated the mean and the variance for us. So we can also draw a histogram to look at all of the data. That's just some summary statistics. So here is a histogram of the data, and so it looks roughly like that bell-shaped normal distribution that you see in textbooks, but not exactly, because this is just one sample, one look at it. The more we do it, the closer we will get to getting a smooth looking distribution. So for example, if I upped the number up here to 5,000, ran this again and drew it again, we're getting much smoother. So as you get larger and larger replications, more and more data, you take out the lumpiness from individual numbers being a little different from that randomness. It starts to get averaged out. Alright, so that is samples of 500 samples of size 1. Now we want to look at samples of size 10. So what we do in our code is we just copy it. It's exactly the same. We're just going to change the name here to sample size 10. And we're going to draw samples of size 10 here from the normal distribution, and we're still going to draw 500 of them. So if we just do that, we can check that we're getting the right size array. So using this shape method there, we should have 500 by 10. Yes, so we have 10 draws in each row, and we have 500 replications of that. And then just as before, we want to calculate the mean, and now we have to be a little bit more careful, because in calculating the mean, we don't want the mean of all 500 times 10, which is 5,000 numbers. We want to take the mean along each row, and so we should have 500 means. So in the mean method, the first element is the thing you're taking the means over. The second additional option that we've introduced here is which axis. So that refers to which axis in the array, sample 10, that we're looking at. So the first axis is the 0 axis, because Python likes to start counting at 0, and that would be down, working down the different rows, so working down a column. We actually want to go across a row, so we want to take the same row and a different item from each of the 10 columns in that row. So that's axis 1, that's the second axis in the array, and so this mean is going to be over 10 numbers, and we're going to do that 500 times for each row. Well, let's check. Yes, so M10, the means of the samples of 10, we've got 500 rows. So we've done it the right way around. For example, if we'd done this the wrong way around and gone down axis 0, then we would have the column averages, and we would just have 10 of those instead of the 500 row one. So that's important, and it's a lot easier. We could take loops over this, but it's nice just to have one command that does this. And then we want to draw a histogram of this. And so again, it looks sort of approximately normal distribution, but there's a lot of noise in there. That depends on the particular draws that we get. We could run it again, of course, and get a slightly different shaped figure. The other thing to notice here is that while the shape might be sort of similar to the one above, up here is similar to the one down here, the axis, the horizontal axis, is very different. Up here, the horizontal axis goes from -3 to +3, because it's a normal distribution with variance 1, so we expect most of the data to fall within plus or minus 2 standard deviations, and almost all of the data to fall within 3, which is what we're seeing there. Down here, this is the shrinking that we were looking for, but you can't really see it on the figure because we've got a different axis. So there's a piece of code we want to get rid of. We should have cut that out. That's floating around from a previous tutorial. So here we can draw the same code, but we will set the axes to be -3 to +3. And in fact, what I'm doing here is what I've recommended to do previously, which is to write down all of the commands to draw a plot with matplot, or at least most of the commands. Up here, it's done pretty much all the steps in one go for us. With the plot histogram command, it's produced counts, bins, and some other options, and then we've just drawn that with plot show. Clearer what's going on if we put out the steps. So the first 2 steps are to draw a figure and to generate some axes for that figure. And so you could do that in 2 separate stages. I've actually collapsed that here, and so with the plot subplots command, with no other additional elements. It's just drawn one axis, or generated one axis, which is empty in that figure. So the axes are called axes 2 and the figure is called figure 2. And that's useful because then I can keep track of the names easily. And now I draw the histogram. So in axes 2 I add a histogram of M10, 30 bins, and I want to have density on the vertical axis. So I don't want to count, I want to have it as a probability or a proportion. And then the second command here is the one that will achieve what I want, which is to set the x limits from -3 to +3, and then finally it will show us the plot. And so now we can see, compared to the first plot, which was also on -3 to +3, that we have a kind of bell shape, but it's much tighter. Here it's mainly between plus and -1. And this is what we're expecting to see with the law of large numbers, that as we get bigger and bigger samples, the samples' averages look more and more like the mean of the original distribution. Within those samples, there'll still be lots of spread, but there'll be some high and some low, and those will cancel out, and we'll tend to get close to the mean on average. So this is 500 means, and they're now very tight. They're not spread out at all. And so we could do this again. We could change the size from 10 up to 100. And plot, and now we can see we're getting much tighter, and then we could do it for 1,000, and now we're very, very tight. And so the mean was 0, and there's very little variation around that mean. Out of these 500 replications, each of them had a mean that was very close to 0, and that's because we're drawing 1,000 numbers, and so that is gives us a pretty good, accurate picture of the distribution. Now the final thing here is, instead of doing this and repeating it, essentially what we did is we worked out our code and then we just changed this size variable here. So in terms of writing usable code, it's nice to have the variables that you're going to want to change pulled out the front so that you know what they are, the parameters of the model. And so then size automatically got changed here. It was only one variable, so it doesn't make much difference, but in terms of code style, it's useful because now I can write a loop very easily. I generate a list of different sizes. I'm only going to use 1, 10, 100, and 1,000, the ones we used above, so I can just generate that by hand with the size list here. And then I'm going to run size, my same command, over the elements of that list. And I just put it inside a for loop, and then the code is basically exactly the same in here. The only thing I've changed is that when I draw the plots, I'm going to be drawing 4 different plots, and so I'd like to know which one they're for. So I say the distribution of sample means, and then the sample size. And so percentage I means it's looking for an integer, I for integer number, and it looks after the quotation marks to tell it what the percentage is. So it's kind of like a little dummy variable holder, placeholder. And so we see here that what it puts in that space where the percentage is the variable size. So it's going to put in the size. So let's go ahead and do that. And in one go, we get the 4 plots that we drew before, and we get them labeled now by the sample size, so it's easy to track what's going on. You could put this in an array of subplots or something like that if you want to make them a little bit more compact to put in a report, but that's the basic piece of code there that shows us how to do it. In the next tutorial, we'll look at doing this without a normal distribution, which is very useful because for the normal distribution, we know that it's always going to be normally shaped. When we use the uniform distribution, we're actually going to see that the shapes are not always bell-shaped. They actually change as we go along. And then we're also going to do a little bit of more fancy stuff, looking at the tail probabilities, not just the means.